out of all part in the calculus, the integral calculus. So integral calculus is considered as the entry point in the calculus. So there are many kind of calculus that is possible, like differential calculus or integral calculus, and then among them there can be many other partitions. But as far as calculus is concerned, that is integral calculus. Integral calculus. Like as far as mathematics is concerned, then mathematics, the entry point of the mathematics is addition. So from addition, mathematics starts. So from addition, mathematics begins. So like that, calculus begins from the integration. So from integration only we have differentiation. Other kind of calculus is differential equation. So that is kind of other area that is considered as the one of the most recent one. There can be other possible. So integration or integral equation or differentiation, differential equation. So these are various parts in the calculus. So integration, integral calculus. What is integration and what is integral calculus? So that is the scenario that we will see. Now I'll give, as I said, that the mathematics, so integration or calculus, it is derived from mathematics. So mathematics is the base of everything. Whereas mathematics term is derived from addition. So addition is the base of everything. Okay. So addition is base of everything. Okay. I am getting this item one time, two time, three time, four time, five time. So this is getting added to me. Okay. So one time this came to me, next time this stick came to me. So I am adding it. Okay, this is addition. So if I receive this 5 times, then 5 into 1, or sorry, 5, 1 plus 1 plus 1 plus 1 plus 1, 5 times. So 5, this I received. If I receive 2 times, then 2 I receive. So I have kind of 5 book and 2 stick added. This is addition. Okay, but when I am receiving this, someone is giving, right? So from him, it is subtraction. So if I get it, then it is addition to me. But person from whom I am getting it, for him, it is subtraction. So subtraction derives from addition. So one way it is subtraction, or okay, so how much I am getting one item, I am getting, okay, so I am getting one item, I am getting one item, in a sense that if I say that if it is moving in this direction, it is addition, then same thing. If it is moving in other direction, then it is subtraction. So negative means same thing which has opposite direction. So that is also called subtraction. So for me, if direction is this, that is inwards, the person from which whom I am getting this, for him direction is this way. So positive and negative, the concept lies in the concept of direction also. If things are moving in one direction and we call it positive, if same thing is moving in other direction, then it is called negative. So that is positive and negative. So negative or subtraction, they come out from the addition one. So addition in other direction is subtraction. So that is addition and subtraction. So basic thing for the any calculation is addition. So like a person is walking, a person is walking. In first hour he walked 1 kilometer. In next hour he again walked 1 kilometer. In next hour, again he walked 1 kilometer. At the end of 5 hours, how many kilometer he walked? So 1 kilometer, 1 kilometer, every hour. So this is 1 hour chunk. In that 1 hour, he walked 1 kilometer. Next hour, he walked 1 kilometer. Next hour, he walked 1 kilometer. Okay. So he is keep on walking. So 1 kilometer, 1 kilometer. Okay. So 1 kilometer in each hour, he is walking 1 kilometer. If that is the scenario, then at the end of 5 hours, how many kilometers he walked? So, as far as mathematics is concerned, everything is addition. If everything is addition, then everything is collection or everything is decollection. Means you are losing the item, that is subtraction, or you are collecting the item, that is item is same. Either it is coming this side or going that side. That's it. So either you are collecting it or you are decollecting. So in that way, when person is walking, first hour he collected 1 kilometer. Like that, next hour he collected 1 kilometer. So in every hour he is collecting 1 kilometer. 1 kilometer into 1 plus 1 kilometer plus 1 kilometer plus 1 plus 1, 5 kilometer total he collected. So what is the distance he covered at the end of 5 hours? That is the collection he made. So what is the total addition? What is the net connection collection? That is the addition. Okay. Now a person, if this is time, this is x-axis, this is time, this is y-axis vertical, and this is collection per hour. Collection per hour. Now if this is x-axis, okay, if this is x-axis, okay, so if this is x-axis, then on the x-axis this is first hour number 1, hour number 2, hour number 3, hour number 4, and hour number 5. In the first hour, he is collecting 1 kilometer. In next hour, he is collecting 1 kilometer. Next hour, he is collecting 1 kilometer. So what is 1 kilometer? So 1 kilometer is the distance. It is the vertical. If this is x-axis and this is y-axis vertical. If x-axis is hour, 1 hour, 2 hour, 3 hour, 4 hour, 5 hour, or 1 hour, 1 hour, 1 hour gap, then if I see the vertical, then this is the how much he is collecting. So if graph is like this, if it is x-axis and graph is like this, okay, this proves that every hour he is collecting 1 kilometer. So in 1 hour he is collecting 1 kilometer. In next hour he is collecting 1 kilometer. In next hour he is collecting 1 kilometer. Next hour. So if this is x-axis, then graph is like this. This is xy plane. If this is xy, vertical is xy plane. If vertical is xy plane, if this is x-axis, then this is the graph. If this is the graph, then this is the how much he is collecting every hour. Okay, then this is nothing but velocity. We call it velocity. Okay, this uh, a person who knows technology, he uses minimal term. This is velocity, and this is acceleration, and this is differentiation, this is differential equation. If you keep introducing new terms, then suddenly it is not considered as good practice. So rather than, I would say, if this is x-axis and every moment is the time, 1 hour, 2 hour, 3 hour, 4 hour, and he is collecting 1 kilometer in first hour, 1 kilometer in next hour, 1 kilometer in next hour. Then at the end of 5 hours, how much he has collected? 1 plus 1 plus 1 plus 1 plus 1. So he collected 5 kilometer at the end of 5 hours. How much is the rate of collection? Rate of collection is 1 kilometer per hour. You can call it velocity. So rate of collection. So per hour, how much is getting collected? So per hour, he is collecting 1 kilometer. Okay. If he is collecting 1 kilometer, then how much distance he has traveled from at any time? So if I say, can you tell me if he starts from 0 kilometer at the end of 3 hours, what is the distance he has covered? So first hour he collected 1 kilometer, next hour 1 kilometer, next hour 1 kilometer. So at the end of 3 hours, total collection is 3 kilometers. So he traveled 3 kilometer distance. Okay, if he traveled 3 kilometer distance, then how much he traveled per hour? Now this is called rate of change. Okay, rate of collection. So if in 3 hours a person is traveling 3 kilometer, then per hour how much? Per hour how much means rate of collection per hour. That is 1 kilometer. If it is 1 kilometer per hour, then how much collection is in 3 hours? How much collection in 3 hours? Reverse is what is the rate of collection per hour? Okay, there are two things. One thing is how much is the collection he is making at the end of each hour. Okay, like at the end of first hour, the total collection is 1 kilometer. At the end of second hour, total collection is 2 kilometers. At the end of third hour, total collection is 3 kilometers. What is the rate of collection per hour? If he is collecting 3 kilometers in 3 hours, then 3 by 3, 1 kilometer per hour. One is rate of change and one is total collection. Okay, both are reverse to each other. If I know rate of collection per hour and I am trying to get total collection, it is addition. Per hour I know what is collected 1 kilometer, 1 plus 1 plus 1 3. If I add all three quadrant of the rate of collection per hour, then it becomes total collection. So if I know rate of change, then if I add rate of change per unit wise, then it becomes collection. This is addition. This is addition. Okay. This is one way of calculating the addition. 1 plus 1 plus 1 in 3 time slot is 3 kilometer he collected in 3 hours. Oh, who will do 1 plus 1 plus? What about after 30 hours? Then 1 plus 1 plus 1 30 times if you do, then he collected 30 kilometers in 30 hours. It's easy, right? 1 into 30 equal to 30. So multiplication is nothing but iterative addition. If I iterate the addition, then it becomes multiplication. So 1 plus 1 plus 1, 1, if I do, someone will say 1 you are adding 30 times, right? Then 1 into 30, straightforward. 1 into 30 is 30 rather than 1 plus 1 plus 1. So multiplication is, if the addition is constant, 1 plus 1 plus 1, repetitive, iterative, then we can go for simple multiplication. So addition has two forms now. One is 1 plus 1 plus 1 or 1 into 30. Through multiplication also, we are trying to achieve addition. Okay, now someone is very smart. He is saying who would do this much? Now, if you know this is x-axis and this is our 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30. Okay, and every hour he is collecting 1 kilometer, 1 kilometer, 1 kilometer. So the collection rate of collection per hour, the graph is like this. So constant. 1 hour, 1 kilometer, this is 1 kilometer per hour graph. This is our line, that is x-axis. The parallel to x-axis, this is y-axis. Parallel to x-axis, if graph is like this, and then interception on the y-axis is 1, then he is collecting 1 kilometer per hour. Calculate the area. Okay, if this is x-axis, okay, so if this is x-axis, if this is x-axis and this is y-axis, and graph is like this, where the constant distance is 1 kilometer, then every hour is collecting 1 kilometer. If that is the case, whatever this is one end and this is another end, this is another end, this is one end. Whatever the rectangle you are seeing, just calculate the area. So one way of doing addition is adding. Another way of doing addition is multiplying. Another way of doing addition is calculating the area. If I know the rate of change, if I can draw in a graph, then from beginning till end, whatever the rectangle I am seeing, that is width into height, if I do, then that is the area. Area is nothing but multiplication. Multiplication is nothing but addition. So we are getting addition in this fashion. So clear, right? So if it is 30 hours from here to here, if it is 30 hours and this vertical is 1 kilometer, 1 into 30 is the area of the rectangle. So he traveled 30 kilometers at the end of 30 hours. Okay. Now there are three ways we calculate the addition. One is we simply add it. Second is if it is addition is constant everywhere, it is 1 1 1 1, same thing, then we can multiply it, or we can just find the area of the rectangle. The way to calculate the addition through area of the rectangle is integral calculus. One is addition, one is multiplication, and third is integral calculus. Integral calculus is nothing but one funny way to calculate the addition through calculating the area. Area in a sense that width of the area is the independent component, that is time. Time is independent, it doesn't depend upon the person walking. Time is independent. You have to catch that time, but time is moving independent always, right? I am trying to catch the time, but time never known that there is a person sitting somewhere. Time goes independent, passes independent. So time is independent component. If I place on x-axis, that is the width of the rectangle, and dependent component that the person is collecting every hour, we place in the y-axis. If I place in y-axis and that is like this, so this graph is in y-axis, that is dependent component. So I would say y equal to 1. Y equal to 1 means at every moment on the x-axis, y is always 1. If it is always 1, then I can draw like this because it is constant 1. Okay? If y is 1 and independent component is 30, then this area is 1 into 30. If area is 1 into 30, this is the way we calculate the addition. Okay, so calculating the addition through area way, when we have the graph equation. Now there is a graph whose equation is y equal to 1, whereas y is dependent component and independent component is time. So irrespective of any time, y is 1. Y is nothing but rate of collection of the distance per hour. What we get when we calculate the area, rate of collection changed to total collection. If I calculate the area of a rectangle where independent component is the rate of collection on which we receive the rate of collection. So rate of collection per hour basis. That is independent component, and the Y component is rate of the collection. Independent component is rate of collection on whom, and Y is rate of collection. If I know the rate of collection and on the independent component per hour, then if I calculate the area, then it is net collection. So if I have rate of change graph and if I calculate the area, then I get the amount on which I calculated the rate of change. This is integration. If I have the amount and if I want rate of change, that is differentiation. Differentiation is opposite to integration. If I know the total collection, if I know in how many hours total collection is made, then from total collection to rate of rate of collect rate of change means total collection per hour. That is the rate. Total collection in how many hours? That is one thing. Total collection per hour. If I have collection per hour from which I am trying to get the net collection, that is calculating the area. That is integration. But if I have total collection from which I am trying to get the collection per hour, that is rate of change, then it is differentiation. Okay. So this is integration and differentiation. If I receive 5 oranges per hour, I am getting in each hour I receive 5 oranges. At the end of 10 hours, I receive 10 oranges. So receiving is 5 orange per hour. If I draw a graph and then calculate the area, then I get how many collection has happened. So from rate to net collection, if I want, then I have to calculate the area. I have to integrate it. But if I know I collected 50 oranges and that is in 10 hours, then how many oranges per hour? Reverse. Then I have to differentiate, divide it, or I mean in better terms. So integration, if I want to calculate the area, it is if area is rectangle, then it is multiplication, better form of multiplication. If I am trying to calculate the rate of change, then it is better division. Okay, division is nothing but better subtraction. Subtraction is nothing but opposite to addition. So main is addition. So mathematics starts from addition. There is nothing called subtraction. If change the direction, it becomes subtraction. That's it. But material is same. It is coming in this direction or that direction. That is the subtraction. Okay. Now integration is understood that if I have rate of change, if I know, and if I draw in a graph, then whatever the area, rectangular area what we see, if rate of change is constant, then it is integral. Okay. So this is integral calculus. Miss, anyone would laugh, right? I can multiply it. Why I'll go with independent component and dependent component and draw the graph and then calculate the area and so many things. Not really. Okay. Now a person is collecting 1 kilometer in first hour. Person is collecting 2 kilometer in second hour. Person is collecting 3 kilometer in third hour. How much he has collected? 1 into 3. Not true, right? Because first hour he collected 1 kilometer. Second hour he collected 2 kilometers. Third hour he collected 3 kilometers. Looks like he is increasing his walking speed. If this is x-axis and this is time, then the y-axis is like this. If this is y-axis, this is x-axis, an independent component that is time, then first hour, second hour, third hour, 1 hour, second hour, third hour. If I see the rate of collection per hour, then it is like this. First hour, he collected total, he collected 1 kilometer. Next hour, the collection is high. See the vertical. So he starts from 0 and at the end, he reached a vertical where the area is 1 kilometer. You get it, right? how much net amount you get, that is the area. So if he starts from 0 and then he is increasing his speed of walking, at the end of 1 hour he is at a speed that I don't know. He at a speed where the net collection of the kilometer is 1 kilometer. Now he is increasing his speed and net collection is 2 kilometer area. He is increasing his speed and in third hour the area net collection is 3 kilometer. Okay, how much he collected? 1 plus 2 plus 3, that will come as 6 kilometer he collected. Okay, now suppose that he is walking at a speed called t. Earlier, if he this is x-axis and he is walking at constant speed 1, means every hour he is collecting 1 kilometer. Now he is walking at speed t. So at time 0, he is not collecting anything. At time 1 hour, so if this is 1 hour, 2 hour, this is 3 hour, at the end of 1 hour, so he is increasing his speed. So at the end of 1 hour, this vertical distance is 1. So at the end of 1 hour, at that moment, the rate of collection per hour at that moment is 1 kilometer per hour. At the end of second hour, the rate of collection at that moment is 2 kilometer per hour. At the end of third hour, the rate of collection, so this vertical is 3. At the end of 2 hours, vertical is 2. At the end of 1 hour, vertical is 1. At the end of 0 hour, vertical is 0. What is the total kilometer he collected? Okay. Now, if this is constantly he is increasing, okay, then how much he collect now? Can some now how much he collect? Can you add it? You cannot add it because at the 0 hour his speed net collection per hour is 0. At the end of zero point 0.5 hour, half an hour, his collection speed is zero point 0.5 kilometer per hour. At the end of 1 hour, you don't know. Now there is no flat. If it is flat, then you can add it. If it is flat, then you can multiply it. Now you have to calculate the area. That's the where integral calculus or area wise, the concept of calculating the area to calculate the amount comes into the picture. Okay, if the rate of collection per hour is smooth, I am collecting 5 oranges every hour, then 5 I can add per hour basis, or 5 into a number of hour in multiplication. Or if I am calculating area, then 5 is the height and number of hours, that much I calculated by area. But what about the collection of the orange is dependent upon the time. It was not dependent upon the time. Every hour, 5 oranges I am collecting. No, it is dependent on the time. So now it comes a rate of collection of the orange per hour is changing hourly basis. That is T. At any time T, the person is walking that many kilometer per hour. If rate of collection per hour basis is dependent upon the independent component time. If this is time, then collection per hour graph is like this. That is 45 degrees because it is T. Then how much he collected at the end of 3 hours? Then blindly you will say, oh, don't worry, I'll collect the area. What is the area? That is said. Now you are thinking, what is the area? I don't know what is the area. Now you will think that if I know the area, can we make it somehow parallel? Okay, if this is the equation, can I make it something like this? Oh, now it is rectangle. If it is rectangle, then I can calculate the area. But how you can stretch this to make it rectangle? because I know rectangle area, right? So if people know that some point, then they will try to pull it to that point so that they can do the stuff. So can I make this triangle? So can I make this line somehow straight parallel to the x-axis? Now I'll calculate the area. Okay, one way I can think of that, if it is 1, it is 3, then in between it is 1.5. If it is 1.5, at 1.5 I can make it straight. So the down came up and up came down. So it looks like some kind of trade-off. Now the equidistance height is 1.5. So 1.5 into 3, that is 4.5. So 4.5 he traveled. Since I know calculating the rectangular area, if I have a triangle, because if dependent component is function over independent component, then it is ft. So ft is t. Means this is what we saw, right? If ft is t, then at t equal to 0, ft is 0. At t equal to 1.5, ft is 1 point. Means y equal to t, 1.5. So if this is in between, this is middle is 1.5, and it is like this, it is like this, it is 45 degree, then here I can tilt it like this. If that is the case, then this is the area. Okay. So now we have height 1.5 and we have width 3. So it is 4.5. Okay. So 1.3 into 1.5. So 3 and 1 and half. So it will come as 4. So 4.5 he traveled. So nice. Okay. Now this concept generally people use in the integration. If you know the area of rectangle, then if you are trying to calculate any shape, if you know the function, then why don't you divide it into many sections? Now we have 3 sections, right? First hour section, second hour section, third hour section. So there are 3 sections, one section, two section, and this is first section, second section, third section. Along the x-axis, hour number 1, hour number 2, hour number 3. Between 0 and 1, first quadrant, second quadrant, third quadrant. Okay. So in the first quadrant, now I can make it straight. In the second quadrant, I can make it straight. In the third quadrant, I can make it straight. So now I have 3 rectangles. Now approximation is better. Error will be less. Okay. So in first quadrant, beginning is 0 and end is 1. So 0.5. 0.5 is the average. Entry is 0 and exit is 1. If I take average, it will come as 0.5. 0.5 into 1. So in first hour, he collected 0.5 kilometers. In second quadrant, entry is 1, exit is 2. If I calculate the average, then I'll get 1 plus 2 by 2. That will come as 1.5. So 1.5 into 1 is 1.5. So 1.5, 0.5 is 2. So at the end of 2 kilometers, he collected 2 kilometers. In the third quadrant, entry is 2 and exit is 3. So 2.5. 2.5 into 1, 2.5. So 2.5 plus 2, 4.5. So he collected 4 points. But these are nice because it is 45 days. Okay. Now this is called approximation. Integration with approximation. Now we cut into, what about, instead of it is t, it is t square. In t square, your average fundamental, whole average fundamental will not work. Now you have to cut down in so many quadrants. Now in each quadrant, you have to see entry point and exit point and calculate the average. Whatever average is, that you make a rectangle. So you will get rectangle like this. One rectangle, then another rectangle, then third rectangle, then fourth rectangle. You understand, right? If this is x-axis, and along the x-axis, you made now 100 chops in the time domain. If it is 100 chop, then at each chop you have the equation of the line. Now that equation of the line, you have entry and exit. You make the average and make the rectangle. then make the average, make the rectangle. So you will get rectangle like this, small rectangle, then bigger rectangle, then bigger. Now each rectangle, you calculate the area and then multiply by, means add it 100 times. Add it all together. That is integration. Means idea is that if you have equation of a line, then how you can calculate the area below it. That is the main concept. If you have a, if equation of a line is like this, that is t square. It start like this and then like this. What is the area below it? Now, if it is t square, then I cannot take the middle and I can make it straight. It will be highly error prone. Rather than that, I can make it 100 chops. In each chop, I will see the entry and exit point. I can make it average. Now we'll get so many rectangles, 100 rectangles. It starts from very small and slowly it will become big. Now approximation is better, because each rectangle has, if it is 10 rectangle, if I make only one rectangle and whatever at the center I'll make it flat, then whatever area we are getting, that is highly error prone because it is t square. Okay, now if I take 10 rectangle, then 10, if I divide it 10 times, then I get 10 rectangle, entry point and exit point. Then everywhere the error what we are saying is small. So net error what we get is very small. So if I say we are dividing into n times, if n tends to infinity, then we are getting infinitesimal small rectangles. Then the, if I calculate area of each rectangle, then the net area that will be very close to what we received. Okay, then I can say it is summation of fx, the width what we are taking now, it is so small that we call it delta x. So fxi means ith component into delta x, whatever delta x is constant. So fxi delta x summation over all the I where it is up to n, where n is infinity, means 100,000, 1,000,000. More n we take, more rectangle we get, and each rectangle, whatever the approximation of the function that we take, that approximation is error is very small. So if I take only one, then error is big. If I take 100, 1,000,000, error become smaller. So at the end, when we calculate the net area where n is very high, then we get kind of matching area with what we get with the actual area. Unfortunately, calculus does not run on approximation. There is a term called ppm, part per million. In a million, if you have error, means 1 by 1,000,000, if you have error, it should be okay. In mathematics, 1 by infinity is also not okay. Mathematics is something on which all sciences they sit. Either it is kind of statistics, or it is electronics, or it is civil engineering, or it is biology, chemistry, physics, everything they sit on. Back engine is the mathematics. So if it is part per million and someone's operation is going on, and and calculation is happening, that one part error happens at that time only, then he's gone, right? Just think about yourself, and so critical operation is going on. I mean, for the sake, you should be all right, but for so critical operation is going on, part per million, out of 10 lakhs, you are the person where the error happened. Can you tolerate this? So mathematics is a science where part per infinity is also not possible. Okay, there not should not be any error. But anyway, concept why do we solve? The concept of calculating the area, when we know the equation, if I don't know the equation area, then we can have so many, because I know the calculation of the rectangle. If I know the calculation of the rectangle, then I can make so many rectangles, and each rectangle's height I can estimate as entry point, exit point, average, and then so many rectangles area. So that will come as summation of I equal to 0 to n, or I equal to 1 to n, fxi delta x, where fx is function over x, or here ft function over t, the ith component, into delta t. Okay, delta t is constant. The strips what we are taking, the width is constant, height is varying because it's a function. So fti delta t summation over I equal to 1 to n, where n, more we keep n, then net summation means net multiplication fti into delta t, that is the calculation of the area of that particular rectangle. So if this is x-axis and this is the curve, then we are dividing into so many small rectangles where width is delta t and height is, if delta t is the width and the time is ti, because I is up to n component we have done. So fti, the height is, the time is ti, then fti into delta t, that is the area of that rectangle. So each rectangle area is growing, so we can estimate the net area. So this is integral calculus basic. At the end, we are calculating the area. So if it is triangle, if this is x-axis and if this is triangle, then how we calculate the area of the triangle? If you are master in calculating the area, integration is used, calculus is used. That's it. Then rather than estimating with so many, rather than whatever you are seeing the equation, just catch the center point and make it like flat like this and make it a rectangle and calculate the area of rectangle and say this is the area. That is one concept. So if you are doing this because you are calculating this end, that end, and then you are making average. If that is the concept, then you can divide into so many parts and every part you calculate the average. So many rectangles will come and error will be less. What is other way? Other way is I know rectangle area. How I can calculate the triangle area? Triangle area is half of the rectangle. Okay. So if this is t and this is independent component and this is y-axis is dependent component and it is ft, that is t, then this is a triangle. This is a triangle. If this is a triangle, then this is a rectangle. If this is a rectangle, then this area is, this is dividing that, there are two triangles, same area. This is half of the rectangular area. If this is rectangle, if this is the width, that is t, and height is also t, then area is t square. If area is t square, then area of this triangle is t square by 2. If it is t square by 2, then t is 3, then 3 square by 2, that is 4.5. So no need to go for approximation. Directly you calculate. That is mathematics. Okay, mathematics never runs on approximation. If approximation hits, I gave the example of operation. If approximation error, if you approximate, there is error out of some error. If error hits on you only, what will happen to you? Okay, so don't go for approximation. Go for substantial thing. Okay, so now it is t square by 2. If it is constant, then it is rectangle. Constant is, if it is 1, then that is t to the power 0. Can you see this? If this is independent component and it is time, and this is dependent component, that is vertical side, and dependent component is constant, that is 1 kilometer per hour he is collecting, then 1 I can call it t to the power 0 also, right? Okay, the area of, if it is 1, the area of rectangle is height into width, that is 1 into t. So if it is t0, equation is t to the power 0, then area is t. Can you see this? T to the power 0, then area is t. If equation is t, then area is t square by 2. If equation is t to the power 1, then t square by 2. If it is t to the power 0, then it is t. This means that integration is whatever the power is, you have to add 1, and whatever is, you have to divide by it. This is mathematics. You have to think in generic fashion. So t to the power 0 means you have to add 1. So t to the power 1 by 1. Area is t. T to the power 1, add 1. T to the power 2 divided by 2. That is the area. t to the power n. Integration is t to the power n plus 1 divided by n plus 1. Now we got the exponential. Now day by day, whatever we are getting, now we'll try to pull it into in this direction and we can have the net area. Okay, so integration is nothing but the if I have the equation of the dependent component, then whatever the underneath area is. So if person is walking at 1 kilometer per hour, then how much he walked between second hour to fifth hour. Okay, then second hour to fifth hour, whatever the area is, that much. So whatever the quadrant you are seeing, that quadrant you have to calculate the area. That is called kind of boundary condition or limiting condition in integration. So integration you limit from one point to other. What is the lower limit and what is the upper limit? By default we calculated from 0 to any t. You can calculate from t1 to t2. So from t1 to t2 means from t1 to end, t2 to end, and you subtract. Straightforward, right? So that is the limiting integration that we'll see. Now we calculated the now concept of calculating the area of a line. Area of a line in the sense that variation in t. T to the power 0 is t. Calculate addition is t. T to the power 1 is t square by 2. If it is t to the power 4, t to the power 4, it will start and go like this immediately. Okay, what is the area? T to the power 4 is t to the power 5 by 5. That is the area. Okay, one more t is coming because we are multiplying by weight. Okay, so we started the integral calculus and slowly we will kind of move on it. But one thing we have learned is if I multiply height by width, then if the height is equation of rate of change, if I multiply height by width, then we get the amount on which we have had calculated the rate of change. So if rate of change is kilometer per hour, collection kilometer per hour, then area is net collection. So that is the integration, another form of calculating the addition. So if I have net collection, from that if I want rate of change, rate of collection, that is differentiation. So if I have t to the power 4 and I am calculating the integration, then t to the power 4 is differentiation, is the rate of change of something else. What is else is t to the power 5 by 5. If t to the power 5 by 5, if I differentiate, I get t to the power 4, then you can calculate the what is the way. If it is integration is n plus 1 by n plus 1, t to the power n is t to the power n plus 1 by n plus 1, then differentiation of n plus 1 would be n plus 1 multiplied by t to the power n. Then only it will become that indeed. Just suppose. Anyway, we will proceed on.